Diving into the world of programming or trying to prep for those brutal coding interviews can feel completely overwhelming, right? But looking through these bootcamp notes on Java foundations and data structures, it actually breaks down into a really clear 12-day progression. So let's unpack these core basics together and see exactly how they build our algorithmic intuition from the ground up.
Here is our roadmap for today's explainer. We're going to start with Java basics and control flow, move into loops and pattern printing, then cover functions and code modularity. After that, we'll tackle arrays and matrix traversals, dive into strings and hash maps, and finally bring it all together with problem-solving foundations. All right, let's jump right into Section 1, Java basics and control flow. Think of these as your raw materials.
Looking at how Java organizes its memory is actually kind of fascinating. On the left, we've got primitive types. You can think of these as the fundamental atoms: int for whole numbers, float for decimals, and Boolean for true or false. They hold exactly one simple piece of information, nothing more. Then on the right, you have non-primitive types, like strings and arrays. These are complex structures that group multiple pieces of data together. Whenever we take an input, say using a scanner, it's going to land in one of these buckets. Grasping this basic difference is literally your first step in memory management.
So, how exactly does Java handle these different sizes of data? Well, it does it through something called typecasting. Imagine you have a small cup of water. That cup is like a small data type, say a byte. Now, imagine pouring that cup into a massive water tank, like a double or a long. It fits perfectly without spilling a single drop, right? That is implicit typecasting. Java just automatically converts a small data type to a large one safely. But try pouring that massive tank back into the tiny cup, and you're going to lose data. That requires explicit permission from you, the programmer. Okay, so we have our data, but how do we actually make decisions with it? Let's ground this in a real-world scenario. How would we order a cup of coffee using conditional code? When you walk into a cafe, your brain naturally processes logic to make a decision. Let's look at how this everyday human decision-making translates directly into computer logic. The really cool part is that human decisions map flawlessly to if-else statements. Our condition is coffee available? If that evaluates to true, we provide coffee. Else, we provide tea. It's strict binary logic. And while we're talking about essential operations, take a look at the modulo operator at the bottom there, represented by that %sign. It simply gives you the remainder of a division. It might look super basic right now, but trust me, it is a critical tool for classic interview questions, like finding a unique element or just checking if a number is even or odd.
Moving right along to Section 2, loops and pattern printing. This is what we call the logic engine. Here is a quick challenge for you. What if we desperately need to print the word hello 1,000 times? Are you honestly going to sit there and manually type that out 1,000 times? Of course not. That's practically impossible, and it'd be an absolute nightmare to maintain. And this proves exactly why while and for loops were invented in the first place. They are our automated logic engines. Let's actually do a dry run of a basic loop right now. We track our iteration, the values of our counter I, our condition I is less than or equal to n, and the action. On iteration 1, I is 1, the condition is true, so we print. But here's the massive catch. We absolutely must update I to 2 for the next round. If we forget to update that counter, well, congratulations, you've just built an infinite loop and crashed your program. This is why you should always track your variables on paper to stay safe. Here's where we get to apply loops and operators together for a super classic coding interview problem, reversing a number. Step 1, we use that modulo operator we just learned, n modulo 10, to grab the very last digit. Step 2, we accumulate that digit into our reverse sequence. And step 3, we shrink the original number down using integer division, n equals n divided by 10. We just loop this exact logic until the number hits 0. It's elegant, it's mathematical, and interviewers absolutely love to test it. Okay, Section 3, functions and code modularity. Think of these as your structural blueprints. If there is one huge takeaway from these notes, it's that Java functions are your ultimate anti-duplication tool. They're basically encapsulated blocks of code that perform very specific tasks. Imagine writing a loop to check if a number is prime. Instead of copying and pasting that entire chunky block of code every single time you need it, you just wrap it up in a function. It immediately becomes this reusable blueprint, wiping out redundancy entirely. Let's quickly break down the anatomy of a Java method. First up, we declare a return type, basically asking what kind of data is coming out of this. If nothing comes out, we just use the word void. Next is the function name, followed by parameters inside parentheses. These are your inputs. Finally, the return statement hands the output back to the main program. So inputs go in, the magic logic happens inside the block, and a specific data type comes popping out. Welcome to Section 4, Arrays and Matrix Traversals. We're getting into the real architecture now.
Notice the clear visual progression here. A 1D array is simply a single row of homogeneous elements. Think of it like a linear list of student test scores. And as the notes point out, if you need that row to grow dynamically on the fly, you jump over and use an array list. But a 2D matrix? That takes our standard array and expands it into a full grid, perfectly organized by rows and columns. To traverse a 1D array, you only need one loop. To traverse a 2D matrix, you're going to need nested loops, an outer loop keeping track of the rows and an inner loop sweeping through the columns.
Now, the notes cover stuff like matrix addition and multiplication, which is great, but let's dive into a much trickier interview challenge. How do we print a matrix in a waveform, meaning row 0 goes left to right, row 1 goes right to left, row 2 goes left to right, just alternating back and forth all the way down? Take a second. How would your nested loops actually handle this physical change in direction? The big secret here? It's all about odds and evens dictating our loop direction. Our waveform logic entirely depends on that row index I. If I is an even row, like 0 or 2, our inner loop just traverses left to right like normal. But if I is an odd row, like 1 or 3, our inner loop has to count backward, traversing right to left. See? We establish the visual intuition first before we even think about writing a single line of code.
Let's look at another classic matrix problem, calculating a row-wise sum. This table simulates a whiteboard dry run. For row I equals 0, our column index j goes 0, 1, 2. The inner loop accesses the matrix values 1, 2, and 3, accumulating them into a current sum of 6. The absolute vital lesson here is that your sum variable must be reset to 0 in the outer loop before the next row begins. Dry running visually like this is the only way to guarantee your logic is totally flawless.
Moving on to Section 5, Strings and Hash Maps. Time for some complex data handling. Here is a massive secret in Java. Characters are literally just ASCII integers under the hood. To count uppercase characters in a string, step 1 is to simply iterate over the characters. Step 2, we check if the numerical ASCII value falls between 65, which is capital A, and 90, which is capital Z. If it does, step 3, we increase our count. You really don't need complex, fancy libraries if you just understand basic ASCII math. You use this exact same character manipulation for checking if a word is a palindrome, separating vowels versus consonants, or solving the classic Beasley string problem. It's just numbers. Next up, frequency queries. To find out exactly how many times element k occurs, you iterate through the array and increment a counter every single time the array element equals k. This exact intuition, mapping an element to its frequency count, is the foundational concept for understanding advanced data structures. If you need frequency, you pull out a hash map. If you just need to count distinct elements without any duplicates, you just drop them right into a hash set. And finally, at Section 6, Problem-Solving Foundations. This is our boot camp finale. Look, here is the absolute core mantra you need to take away. Always dry run your logic on paper before coding. The actual syntax and typing out the code in Java, that is entirely secondary. If you cannot prove your algorithm on a piece of paper using tables and step-by-step logic like we did today, you are honestly not ready to write the code. Paper first, keyboard second, always. So, we've unpacked this whole 12 days scaffolding together, from memory and loops to matrices, strings, and hash maps. But here is the real question for you. Now that you can actually see how human logic translates into machine blueprints, are you ready to pick up a pen, paper test your own algorithms, and absolutely crush your upcoming coding interviews? The roadmap is laid out right in front of you. Time to get to work. Thanks for exploring these notes with me on today's Explainer, and I'll catch you next time.